So welcome everybody to my talk on robot athletes. I'm glad you could join me. It's going to be about an hour's worth of talk, and unfortunately due to the COVID pandemic now raging in Taiwan, I will have to record this talk, but if you want to ask questions afterwards about our research, then please let me know and send me an email, which will be on the first slide. So I'm going to start talking about our robot athletes, and you can follow the presentation on jackiebaltis.github.io robot athletes if you want to. If you have problems with seeing any of the slides, also the links to the videos are all given in there as well. So my research for the last 30 years has been mainly on intelligent robotics, in particular humanoid robots. So for humanoid robots we focus on mainly three topics. One is the walking on two legs, which is a difficult challenge for our robots, in particular because using the standard DC motors that are the most affordable and sort of practical way of building a humanoid robot, we have very poor power to weight ratio. So our robots are all walking like 150-year-old wood. The torque in the ankle is about 1/10 of the torque that you have in a human. So that is still an interesting research topic to explore. When we started in 2002, walking on a flat surface was a challenging problem. That one now has been solved by many different teams with many different algorithms, so we've made good progress in that area. So we have expanded our horizon and looked at other challenges like walking on uneven terrain, walking through a forest, trying to climb up, to go hiking in the mountains. Those are still beyond the state of the art. And also push recovery, being able to recover from hitting an obstacle or hitting another person. I'm interested in complex motion planning because humanoid robots, with their many degrees of freedom, make it impossible to pre-compute as parameterized motions all the motions that are necessary to deal with the domain. So for example, if you want to play soccer with your humanoid robots, then all you really need is about a dozen motions, like walk forward, walk backwards, turn left, turn right, kick with the right leg, kick with the left leg. But I can give that to a graduate student of mine, and 2 weeks later we will have a complete set of motions for our soccer playing robots. But the problem is this is only a very small set of the possible motions that a human could develop. So for example, for myself, when I started working at National Taiwan Normal University, I was in the other building, so my office had a special door that included two spring-loaded latched locks. So in order to open the door, I had to turn the knob and I had to twist the key in the lock. Now if I have both hands free, that's not a problem because I can just do that. But when I carry a laptop, then that wasn't possible anymore. So the way that I managed to solve that problem, because I didn't want to put the laptop down every time I wanted to open the door, was that I use my knee in order to push against the knob. So I turn the knob, I put my knee against it, So now that part is fixed, then I can use that same hand to open the latch, and then I can enter the door. So the interesting thing about that is that if I ask one of my graduate students that we need to have motions in order to open a door, then there's no way they would predict that this would be a reasonable motion, or that that would be a motion that is necessary to open a door. So we need to have robots that can plan complex motions like this online without having detailed knowledge about what the environment is going to look like. They need to be able to calculate those motions on the fly. They need to be able to generate these motions. They need to make sure these motions have a reasonable chance of success, and these motions are under constraints, kinematic constraints, what I can reach, and dynamic constraints, the parts where I'm still balanced without falling over. Lastly, we're interested in human-robot interaction, programming by demonstration, because for our robots to be useful, they need to be able to interact with humans, which means they need to be able to interact, they need to be able to understand human speech, they need to be able to talk, they need to have text-to-speech systems. Their speech, however, also needs to be reasonable. So if your uncle asked the robot, "Where are my glasses?" and the robot would answer saying X is 3.2 meters, Y is 1.7 meters, and Z is 0.8 meters, then that answer may be correct, but it would be very useless for a human, because they don't think about their space around them as a three-dimensional Cartesian coordinate system. So instead the robot would have to say something like they're beside the television or on top of the table in the kitchen. And also the robot needs to be able to understand and generate gestures, so they can say like, robot clean over there, or don't do this, or something like that. Now, those are very long-term goals. There are significant research challenges associated with each and every one of them. In order to make sure that we're actually progressing in the research that we're doing, and as a motivating example for the research, I've been very much interested in robot competitions. I think we do need to have good benchmark problems, but full applications are not practical at this point in time. So for example, one of the things we would like to do is to develop a robot fireman. But if I then say, oh, I want to find out which research team, MIT or Stanford or KAIST or NTNU or NTU or CCU has the best algorithms for that, then a test would be to say, okay, it's easy, we just put a house on fire and then put in the robots and see how many of them come out and how many victims they can save. Then that is just much too hard. At the moment, none of the robots are going to be able to do any kind of saving of people out of a burning building. The technology just is far away from being able to do that. So then everybody scores 0, and we still don't know who did a good job or which kind of research is likely to lead to better, more efficient systems in the future. So we need to have smaller problems that we can work on and that we can compare performance, benchmark problems. And I think robot sports in particular are a very good research benchmark problem, and also have led in my personal career to many insightful advances to the state-of-the-art in those areas. So the outline of my talk, I'm going to tell you a little bit about our humanoid robots, and then I will describe some of the research topics that we we're working on in recent years. I will give a fairly high-level description of how we achieved those research results, and then I'll make some concluding remarks to summarize our contributions. The Educational Robotics Center, ERC, at NTNU, we are quite an international group. We have visiting researchers, PhD students, and postdocs and MSc students from several other countries, including France, Germany, Brazil, Indonesia, and Korea. The humanoid robots that we use, our smallest humanoid robots, are based on the Darwin platform from Robotis. They're about 45 centimeters tall, 3 kilograms in weight, and 22 degrees of freedom. As I said, we believe in robot competition, so we've been actively taking part in many robot competitions. And Yes, I should move myself to there. We won the second place in the Eurocup all-round competition. I'll go into more detail about that competition and what the robots have to do in 2019, which was a good success for us. Okay, there's not so good either. Maybe here. Our next larger sized humanoid robots are the Robinian robots. They're 80 centimeters tall, 7 kilograms, 26 degrees of freedom. The special thing about those robots is that they use a parallel kinematics design in order to make the legs lighter, so there's actually no servo motors in the knee joint of the robot. They're placed in the ankle and the hip, but then you have to double them. These robots won the first place at the Eurocup competition and also did well in several other events. We have a 1.3 meter tall humanoid robot, 12 kilograms with 20 degrees of freedom, which is specifically built for the RoboCup soccer competition. And our largest robot is Robotis Thormang robot, 1.3 meters tall, so about yay height for me, and 42 kilograms. 31 degrees of freedom, also has some more advanced sensors, gyroscopes, accelerometers, but also force and torque sensors, and is by far our most capable but also our most expensive robot. And we have been doing human-robot interaction research with this robot mainly through previous years, where we did well in the magic competition. So now, when it comes to designing these competitions, it's actually quite difficult to come up with good benchmark problems. And in my view, one of the things that anytime you start setting up one specific challenge, then teams will optimize for that particular task. So I very strongly believe that robustness and versatility are important aspects of intelligence, and that we need to challenge our robots to do that. So in particular with humanoid robots, if you want to solve one particular task, you usually never end up with a humanoid robot design, because if I want to deliver mail in an office, then I build something with wheels, and it will be much faster and much more efficient than a humanoid robot would ever be. And if I want something to clean the windows, then I build something with suction cups and a sweeper, and it will do a good job cleaning the windows. Humanoid robots are only useful, or are only come to be very are necessary. Humanoid robots only come to shine when you need to have a single robot that can perform many different tasks: deliver the mail, pick up the garbage, clean the windows, wash the dishes, save people from a burning building, drive your car to the parking lot. Then humanoid robot makes sense. And for specific kinds of problems, narrowly specified domains, it's quite easy for robots to outperform humans. Where robots are bad at, even today, is that the kind of intelligence that is needed for vast different kinds of environments, like the general vision problem. Building a machine vision system that can measure the size of drill holes in a workpiece is much easier than being able to write a vision system that can detect or distinguish a dog from an elephant in all images, in all kinds of lighting settings and things like that. So the robot competitions provide a crucial benchmarks for us for guiding our research, because another thing is you cannot cheat there, right? At 9 o'clock the referee is going to blow the whistle, and then your robot has to work. Sometimes videos that you see from robots performing certain feats, they're impressive, but you only see the one successful try. You don't know if they only tried it once, took a video and that's it, or if they tried it 10 times or 100 times or 1,000 times before it finally worked, and they now post the video. So combining sports and robotics is a very natural way for us to motivate teams and spectators, and also later on I'll see it gives a very nice qualitative measurements in order to evaluate our research. So I'm the president of the Federation of International Robot Sports Association, FIRA, and we have several leagues where we have various robot athletes competing against each other. The event is quite nice, quite large. We had 1,200 participants in 2019, but then 2020 we were unable to host the actual event because of the COVID pandemic, so we actually had a social distancing competition which was online only. So there are several different leagues for humanoid robots playing soccer with a global vision system, for drones, for high school children, for wheeled robots. They're all included in the FIRA group of competitions, but we're mostly interested in the FIRA Eurocup, where the challenge is for a single robot, and I already mentioned that before. I think having to do more than one task is crucially important for intelligent systems. Not just being able to specialize on one particular domain, but being able to reason about the world around them in many different kinds of scenarios is very important. So in the Eurocup, it's a decathlon, so it's 10 events: archery, sprint, marathon, obstacle run, united soccer, triple jump, Spartan race, weightlifting, basketball, and the mini rescue robot competition, mini DRC. And a single robot has to compete in all of them. Now, that in itself makes it a very interesting competition, because it turns into a system design challenge. For example, for the sprint that you'll see in a minute, you need to clearly, the idea is to have robots that can run as fast as possible, so you want to be as light as possible. So you want to have the smallest battery that lasts for the 30 seconds that it takes to finish your sprint. But for the marathon you need to run 400 meters, and now you're not allowed to change your battery, so you need to have a very big, very powerful battery. So you need to find the weakest link in your performance and try and optimize for that. So you need to find the right balance between endurance and sprint capabilities. And one of the future applications of our robots is as rescue robots. If you sort of look another 30 years into the future. So one of the events at the FIRA competition is the weightlifting competition. So there, similar to human weightlifting, the humanoid robot has to carry a heavy load. However, we did not just want to test the shoulder strength, the strength of the shoulder servos in your robots. So it is actually more of a balancing competition. We have the video here. The robot first needs to walk up to the bar. Now these robots are all real robots. They are fully autonomous. They're not remote controlled by humans or something like that. Once the robot positions itself so that it is able to pick up the bar, then it needs to walk to the third line from there. Now with one foot touching the line, the robot now needs to lift the weight above the head. And this is where the balancing comes into play, because for the first 50 centimeters, the center of mass of the robot is very low. So it's a very stable walking gait. Now the robot has to be able to compensate for the shift in the center of mass. So now the COM is much higher. And you can see the walking gait has changed. It needs to be able to compensate for that. Next, the sprint. And one of the nice things about using sports is that even without it's very easy for people to understand what the point of a competition is. I already talked about the sprint before, and I didn't really have to say anything else. And each and every one of you understood that the idea is to run as fast as possible for short distance. So you may not have known whether it's 2 meters or 3 meters, but it was clear there was a short distance. And what capabilities of the robot we're testing in this scenario. So let's have a look at the sprint.
We will start the sprint final in 5, 4, 3, 2, 1.
This was the FIRA 2017 competition. One of the robots did a false start, so they had to be pulled back, everybody. So in a sense, it's just like the Olympics. The atmosphere is very electric, people are very nervous. Another good thing about using robot sports as competitions is that we can track progress. So you see the robots here from 2017. The world record in 2015 was about 52 seconds, and then 2017 the record is 26 seconds. And even in just 2 years, you can see how much the technology improved, how much faster the robots now are compared to just 2 years ago. And we have the Spartan race. This is an extreme mobility challenge where the robot has to climb a rope and climb a ladder, you know, and that challenges the motion planning, because for climbing the ladder and the robot needs to, the spacing of the rungs is not fixed, so the robot needs to be able to see where it can reach and which holes are stable, and then plan a path through there. So this is not something that you could pre-compute with a set of parameterized motions, because there's just too many variables. Obstacle run is a navigation challenge where the robot needs to find the exit, needs to map its environment and then walk through. Marathon is always, in contrast to the other robot competitions, to the other Eurocup events as well, is always held outdoors, so that makes the vision problem a lot more challenging. And the robot has to follow a path which is indicated by the red tape. Actually, it can be any color tape. And also since 2019 with markers, so there's a right arrow and a left arrow and a straight ahead arrow. And then has to walk for 425 meters, which is exactly 1/1000th of the marathon distance. When we started the competition, the distance that the robots had to walk was 42 meters, because that's how far they could walk in an hour and a little bit of time. So again, you can see how much the robots improved. We have a triple jump, which is the highly dynamic motion, where the key aspect is to be able to synchronize all your motions, so all the joints are using full torque at exactly the right time, and then you need to be able to land. So that's a quite interesting challenge. In particular, when we started it, we built the playing field to be about, I think the maximum distance for the jump was that we expected was sort of 20 centimeters, so we built it for 50 centimeters, and then one of the teams showed up and jumped 80 centimeters, so they jumped out of the stadium. So we had to reconstruct the stadium then for the next year. Basketball, now it would be really cool to build a robot that can dribble a ball, but that's not really possible with the technology at the moment. So the robots for the basketball are mainly dunking and throwing the ball for 3 points or 1 point or 5 points. There's 3 different circles. How far away you are from the basket determines how many points you will score. Archery, we have a moving target, and then the robot has to hit the target. This is actually an interesting problem too in motion planning, not because of the huge variety of motion, but because of the high precision that you need in order to be able to hit a target. And with our largest humanoid robot, the Thormang, we are actually trying to qualify for the Taiwan national archery competition and for the Olympics. The goal was in 2020, but because of the COVID now it's delayed until 2021, but we were slowed down as well, so we hope to be able to compete in an Olympic archery distance event in 2022, next year. Here's our archery robot shooting 15 meters.
Shooting.
And you can see it's quite accurate there. It so over 15 meters we are quite accurate. Mainly it's due to our detection of the target, which is quite stable. We use a histogram of oriented gradients for detecting the target, and then train a classifier using support vector machines in order to classify targets. But for the Olympics we have to shoot 75 meters. So that requires an accuracy of better than 0.4 millimeters. And the main problem right now is that we're using the bow that we have, we cannot exert enough torque in order to shoot that far. The furthest shooting that we've done was at National Kaohsiung University of Science and Technology for 45 meters. So it requires more work. Now, the sports events as quantitative evaluation of the performance of the robots are very good. For human-robot interaction, however, it's hard to come up with a quantitative measurement. And since 2017, I sort of thought that for a lot of the AI research, there hasn't been enough focus on attention, because I think attention is crucial to human intelligence. But for example, the deep learning systems at the moment, they all look at the image as one shot, and then we expect it to spit out everything that's in the image, or whether there is a cat in the image or not. But a human visual perception doesn't work like that at all. If you look at the image on the right here, whether you see a grandma or a young lady looking away from you depends on which parts of the image you focus on first and how you interpret those parts of the image. So if you look at this here first and you see this as an eye and this is a nose, then this image will turn into a grandma. And if you look at this and you see a chin here and a neck and a necklace and an ear here, then it will be a young lady looking away from you. And this is the kind of thing that we haven't done much. There hasn't been much attention paid to it in AI research in general. So we came up with the idea of the Robot Magic Show, which we usually hold during IROS conference, the largest robot conference for researchers. Now, I like Magic as a testbed for human-robot interaction, but also because Magic is all about misdirection of attention, right? I want you to look here, and this is where the trick happens. So here are two of my favorite magic tricks with our robots. So this is a nice psychological trick. The robot gives a coin to the spectator. The spectator has to put the coin behind the back and then either put it in the right hand or the left hand. So then the robot asks you and tries to guess whether the coin is in the right hand or the left hand. So this is actually the part where the trick happens. The robot is trying to look for cues, but Some people claim that you twist your head slightly in the direction of where the coin is not, or that your eyes flicker. Those will be very difficult to detect using the webcam that we have mounted on the robot. And even though we're training on that, if these hints are not conclusive, then the robot is asking you to cross their arms. And for most people, and we're about more than 80% accurate with this, if you ask them to cross the arms, then the coin is in the arm that is below. People are trying to hide the coin subconsciously. Now, being able to detect which arm is on top is easy for humans, but we tried it for about 6 months using and it's actually quite a hard problem. So we finally ended up using the laser scanner. We wish we could have just used the camera itself, and we're still doing research trying to improve on detection using the camera. Now you can see here the output of the LiDAR scanner and what the robot actually predicted. So here's the point cloud of the person. And here's the same trick during the official competition.
Put it behind your back and hide.
I also like the next trick, which is a nail trick, so it's more dangerous if we do it wrong. I, in particular, would be injured. So there's this extra element of danger. The trick includes some comedy, since I assume most of you are able to speak Chinese, you'll be able to understand it. But the whole trick is sort of based on the fact that I'm unable to speak Chinese. So we're pretending that the students are trying to trick me.
Welcome everyone, I am Thorming. Today I am going to show you a magic trick that I have learned recently. As you can see, there are 3 paper bags in front of me. Later, I will put this wooden base with a sharp nail into one of the paper bags, and then swap around the position of the bags. To make sure we won't find out the bag is empty by feeling the weight. So I prepared 2 wooden bases without nails. Student, please help me put these 2 wooden bases into 2 paper bags and close it.
So our research goal here is detection and manipulation of soft, deformable objects, because the paper bag is not solid, so you cannot just squeeze it.
Student, please ask an audience member to examine the nail and make sure it is real.
Now you can check.
So, audience volunteer, can you confirm to the rest of the audience that the nail is indeed real? Okay, thank you. Student, please place the nail inside the last bag and close it. And everyone, please pay attention and remember which bag contains the nail. Now, I need another volunteer.
Any volunteer?
Thank you for volunteering. Now, do you remember which bag contains the nail?
So this is important now. So the bag with the nail is the middle bag, right? We're going to shuffle them, but the robot, because it has very fine vision, it can detect where the bag is basically.
You mean this one, right? To make sure that I won't be able to know which bag contains the nail, the student will start swapping the bags around. When I say start, the student will begin and volunteer. You can shout out stop any time you want.
So you just need to say stop.
Let's start.
Stop.
Okay, now I need some time to feel where the nail is.
因为我们老师他听不懂中文，然后就说我们只有1个礼拜时间可以做这个魔术，所以我们就让机器人知道说一定会在中间，因为刚刚你看到是在中间没错嘛，那就麻烦等一下的时候帮我们讲左或右。
哦 ，OK。
对，选择的时候，因为他等一下问说哪一个袋子里面没有那个铁钉没有铁钉，然后他会让老师去按那个没有铁钉的袋子。所以待会一定不要选中间。
Everything okay?
Oh, I am 100% sure where the nail is. So I would like to play something much more interesting. Jackie.
Oh.
As the supervisor of your lab, do you believe in my talent and your students' ability?
Not so much my students' ability, but their hope to graduate, I think.
Oh, I am happy to hear that. Since you trust us so much, we can raise the stakes. How about we use your hand to press down on the paper bag?
What? I'm not so sure about that. It was supposed to be Green's hand, not my hand.
Please give me your hand, Jackie.
Okay.
Volunteer. Choose a bag you think there's no nail inside. Left, right, or middle. Choose wisely. We would.
So now they basically suggested that people should not use the middle bag, right?
You want our professor to get hurt, right?
Left.
Okay, left.
So that volunteer was nice. He didn't want to destroy my hand. Okay. You sure about this? Oh! Okay.
Jackie, don't be a bit nervous, don't you trust me? I am the only hope of graduation for your students. They won't disappoint you, trust me.
Okay.
Hey, volunteer, what's your next choice?
Right.
Left or right?
Right.
Okay, right.
Yeah. Because everybody thinks the nail is in
What
just happened? Is in the middle bag.
Finished rebooting.
Oh, okay. So now we think that there's a error in the robot.
But I don't think this one is safe. Jackie, do you trust me?
No, not really, no. You just rebooted.
Why? I only made one mistake.
Yeah, but you see
Why
my
don't
other
you
hand.
give me another chance?
I only have two hands.
Well, here.
So now the
We
audience.
forgot to put the cap on. That's the problem.
Yeah, got you. Ha ha ha. Don't be that scared.
So now the audience expected me to be injured. I'm disappointed nobody tried to stop it. But the nail, they all saw the nail go into the middle bag, and now magically
I know what I am
the
doing.
nail jumped to the other bag.
So you might be really curious where the actual nail is, right? Jackie, please help me to check what is in the bag.
So you can check.
So this is a very fun magic trick, especially because we can play it in Taiwan, or because people there speak Chinese. People here speak Chinese, yes. So I'm gonna move a little bit quicker. We also have another human-robot interaction problem where we're playing a game of Dr. Eureka against other humans, other players. I want to finish off by talking about our Gogoro scooter project. This project, the goal is for the Thormang robot to be able to learn how to drive an electric scooter and to be able to pass the Taiwan driver's license test for scooters. And that would be pretty cool because it'd be the first time that a autonomous system would pass a driver's license test like that. So at the moment we just started the project, so one of the problems that we have is being able to make sure that our control is accurate enough and fast enough to be able to balance the scooter, because driving on two wheels, of course, similar to walking on two legs, much harder than driving on four wheels or walking on four legs. So here we set up a test to estimate the accuracy in steering control by turning to 5-degree increments on the steering column. And then we use a laser pointer that we project on there to be able to see how accurate the motion is. And this is quite accurate, however it's only half as fast as a human. So we did some experiments with humans driving the scooter and how fast they need to move the steering column to remain balanced. And now we do some larger motions. We also implemented a simulation of our robot in the NVIDIA Isaac Gym for reinforcement learning, and we trained the system in order to learn how to control the scooter given different perturbations. So I'm not sure if we have this video, but we also throw boxes at the simulated scooter while it's driving in order to make sure that the control is robust. Now for the scooter, we also have designed a simulator and a simulator game that we want to play during the FIRA 2021 social distancing edition. So we have our simulated robot driving an environment that matches the Taiwan scooter driver's license test. This is a first prototype with just the ground plane. So you have to do a hook turn here and then change lanes and then do a 180-degree turn, and then there's a stop sign there that we just blow through, and then this will be the end. And just yesterday okay, So
I
here finished.
last time I showed you the app that I wrote that we use in order to control the scooter, the real Thurman on the real scooter.
So this is a app that I
so
wrote where
now
we can control the steering
I
angle for more tests
a whole
on the
bunch
real
of other
robot.
code.
But now I also changed it so that
And,
we can run
what-
it on the simulator.
Have to be
So now you can see the scooter
you can use
and
the Flutter app to
you can control the scooter.
browser. Now this is done by running a WebSocket client, which gives us a TCP/IP connection and a broadcast server written in Python.
So
now
now,
you can see
a little bit hard to see, but there's a traffic light there, so I had to wait for
Of the
the
scooter
light
with
to
my
turn green.
And
Then I can progress.
I cheated a little bit because I made it very slow, so that I have a chance. Failed.
This first part here is the slow driving
So,
part
this
of
is a
the
Flutter
driver's
app
test.
running on the
You have to
phone,
drive 15
3DS
meters
and
in a
JavaScript
40
running
centimeter
in the
track.
browser.
And it has to take you more than 7
Bridge
seconds. And
between
from what my
UDP
students tell me, this is the
and
hardest part
WebSocket.
of the
But I
scooter
think
driving
that,
test.
Proxy we should probably re-implement in Go because
So if you're interested in that kind of research, the kind of systems that we developed, I didn't go into the technical details, but we use histogram of oriented gradients in order to track our targets in archery. Our latest system actually uses deep learning, so we also keep improving them, but that is not as robust for the all different kinds of targets. The problem is not so much the deep learning network, but the fact that we just don't have enough training data for training the deep learning network on all the different archery targets that it may be asked to recognize. For the sprint event, we implemented a visual compass, which is based on using histograms of the top of the image, because those are the part of the scenes that are far away. So as the robot walks, they won't change much, and they allow us to detect the yaw of the robot, which is really the crucial part of the sprint event. And we want to use the same thing on our Gogoro scooter, because so far I haven't talked much about the throttle control, but in order to be able to steer the scooter, not only do you need to have the right steering angle, you also need to have the right velocity, and those are related, and so we need to have a very high accuracy measurement for the velocity, the linear velocity of the robot scooter combination while it's driving. Motion planning for manipulation of soft objects for the magic show, a edge version of YOLO version 4 that we used in Dr. Eureka, various reinforcement learning algorithms applied, both DQN and actor critic and soft actor critic, when we were dealing for our Gogoro scooter project. And I was also trying to convince you about the importance of meaningful robot competitions as a benchmark for research, but also for inspiration of new research directions. Now, if you're interested in those kind of events, then I welcome you to take part in the FIRA 2021 Social Distancing Edition, which is going to be held from the 9th to the 13th of August in August. It's going to be online, and it includes various games for the FIRA community. So one of them will be trying to pass the scooter driver's license test using our simulated Gogoro scooter. There's a scavenger hunt and a teleoperation competition for humanoid robots, a dance competition. And then in December we will host the actual FIRA competition with Eurocup. It's still planned to host it with real robots in São Luís in Brazil. But given that we foresee that a lot of teams are going to have trouble traveling by that time, it will actually be a simultaneous robot competition through various centers in the world. So Turkey, Taiwan, Brazil will all host competitions, and then they're all going to take place at the same time with the same referee, but the robots will be in physically different locations. That's one of the, that's not ideal, but it's one of the concessions that we will have to make, most likely due to the pandemic seemingly not getting better, and certainly here in Taiwan it turned much worse in the last week. So it's easy to see how quickly the situation can change just from one week to the next. And so I'm gonna conclude by saying I wish you all stay safe and healthy, most importantly, and I hope that you enjoyed this talk. So if you have any questions, then please send me an email. At jackiebaltis@ntnu.edu.taiwan. So thanks for your attention, and bye-bye. Bye-bye.